Here's problem 519. Two blocks are accelerated across a horizontal frictionless surface as shown, but frictional forces keep the two blocks from sliding relative to each other, and the two move with the same acceleration. If F is equal to 1.2 newtons and M is equal to 1 kilogram, what is the horizontal component, frictional force, of the force on the large block, on the small block? Alright, so to do this, we really would want to find the acceleration of the system, and the internal forces between the large block and the small block are interfering with that. So let's just blob the whole thing together and worry about the whole system together so that we can find the acceleration. So with this blob of 3m, we have an external force of F to the right. Of course, there would be weight, and there would be a normal force, but those are going to be transverse to the motion as the acceleration is to the right. So there's our free body diagram of the blob. And as we set up Newton's second law for that, we have the summation of all the forces in the x direction is equal to the total mass times A, which would be 3m times A, and that is equal to the net force in the direction of positive acceleration, and that's going to be equal to F. That's it. Just F. So the acceleration is going to equal F divided by 3m, which will be 1.2 newtons divided by 3 times 1 kilogram, 0.4 meters per second squared. Okay, so that's our acceleration to the right. Now, if I did a free body diagram of the big block, the 2m, I would label all the external forces acting on it. It's got weight equal to 2mg. It's got a normal force of the surface acting on it like this. In fact, there's a normal force of the block above it acting down on it like this. And then it's got this F force pulling to the right. It also has, because of this normal force of the block pushing down on it and the surface between it and the small block, there will be a force of friction against the motion like this. And as a result of all these forces, it'll manage to accelerate to the right with a value of 0.4 meters per second squared, as we just found. So that is our free body diagram for the large block. If we were to set up Newton's second law based on this, we would say that the summation of all the forces in the x direction is equal to 2m times A, and that is equal to the net force in the direction of positive acceleration, which would be to the right. So that's going to be equal to F minus the frictional force. So in other words, the frictional force acting on the large block is going to be equal to F minus 2ma, which is going to be equal to 1.2 minus 2 times 1 times 0.4, which is going to be equal to 0.4 meters per second, 0.4 newtons, 0.4 newtons, and it will be to the left, like that. So that is the force of the small block on the large block. Now we want to find the force of the large block on the small block. Well, we know from Newton's third law it should be equal and opposite. So it should be 0.4 newtons to the right. But if we were to prove that, we could do a free body diagram of the small block, and it has a mass m, and it's got weight equal to mg, and it's got a normal force, it's called N1, and it's only got one force horizontally, and that actually is going to be this frictional force that is actually pulling it to the right. That's the frictional force between the two blocks, and it's actually pulling this block to the right with an acceleration equal to 0.4 meters per second squared. Based on Newton's second law for this, we'd say the summation of all the forces in the x direction is equal to ma, and that's equal to the frictional force in the positive x direction. So the frictional force will equal 1 kilogram times 0.4 meters per second squared, 0.4 newtons, as before. And this force is to the right. So that is the force of the large block on the small block, a frictional force of 0.4 newtons to the right, equal and opposite to the frictional force that the small block exerts on the large block of also 0.4 newtons.